Hey guys, welcome to the first of the series of lectures on methods in cognitive science and neuroscience. So this is a short lecture that sort of poses a thought problem for you guys. Okay, so this thought problem is called the Monty Hall problem. Now, it was introduced by Steve Selvin. He's a statistician at UC Berkeley in the 70s. He published a letter in the journal American Statistician, and the letter was called A Problem in Probability. And basically, he posed this Monty Hall problem in the letter. Now, the problem mathematically is very similar to the three prisoners problem and the Bertrand's box paradox. You can look both of those up. They're very interesting. But it was designed after the game show Let's Make a Deal. And Let's Make a Deal, back in the day, was hosted by this fella here, Monty Hall. Nowadays, it's hosted by this fella here, Wayne Brady. So this problem was never actually posed on Let's Make a Deal, but because it was designed after it, it was coined the Monty Hall problem. So let's have a look at the setup of this problem. Okay, so you have three doors, okay? Behind one of these doors, you're gonna find a car. That's cool. Okay, behind the other two doors, behind each of the other two doors, is a goat. A goat as in like sheep and goats. Now, the first thing you do, Monty says, or Wayne, you choose who your ideal game host would be. Okay? He's going to say pick a door. We're going to pick door number 1. Now, before he opens up door number 1, he opens up one of the other two doors. And he says, okay, before I open up door number 1, I'm going to show you this door. Now I want you to tell me, would you like to stick with door number 1, or do you want to switch to door number 3? Okay, so that's the problem. What would you be more likely to do? I want you to think about it. Would you stick with door number 1, or would you now switch to door number 3? I'm not really sure it would matter for me because those goats are freaking cute. So either way, it's a win for me, car or goat. But okay, think about it for a little bit. And let's talk about this. Okay. So people tend to think of the situation in a couple of ways. Okay, they look at odds, which is great. You should be looking at odds, right? And they look at the odds for any of these doors individually being the winner. Okay, so the odds for each of these doors before the reveal is like 33.333 infinity repeating percent, right? So a third odds for each of these doors. Now, you pick a door and another door is eliminated. Now the odds might change, right? But for some people, they don't. So some people say it doesn't matter that this door has been eliminated. Each of these doors still has a 1/3 probability of having that car behind it, okay? Because that's what we started off with, and we can't forget the history of the problem when we're talking about statistics and mathematics. Okay, fair enough. Some people say, well, but yes, it does. The probabilities do change. Okay, so you've eliminated a door, so now this problem goes from a 3-door problem to a 2-door problem. So now your probabilities are half and half. So in each of these situations, I'll get back there eventually. In each of these situations, there's no need to switch, right? So in this first situation, the probability between door 1 and door 2 is 1/3. There's no need to switch. In this situation, the probability is a half and a half. For different reasons, there's still no need to switch. Now, let me pose this to you in a different way, okay? Let's do all the permutations for this problem. Okay, so we're going to look at all the possible door scenarios and the possible choices that we have once we have those scenarios presented to us, okay? So we've got our 3 doors. Here's our first scenario. You can have a lose. You can have a lose, lose, win, right? You can have a lose, win, lose. And you can have a win, lose, lose, right? So you can have a goat here, and a car. Goat here, and a car. And goat here, and a car, right? Those are the permutations. That's how these 3 doors can exist. Okay, so now it doesn't matter what door you initially choose, okay? You have a 1/3 shot at a win and a 2/3 chance of loss. Okay, so you got a 1/3 shot of a win here, you have a 1/3 shot of a win here, and a 1/3 shot of a win here. So if you were to pick and stay with any one of these doors, you have a 1/3 chance of winning. Okay, all right. Now let's look at our possible choices. We can either stay or we can switch. So let's look at what happens in each of these scenarios if you stay versus if you switch. Okay, scenario 1, if you stay, you get a goat, right? If you switch, you get a car. Scenario 2, if you stay, you get a goat. If you switch, you get a car. Scenario 3, if you stay, you get a car. And if you switch, you get a goat. All right, so what's the probability of a win if you stay? Well, it's identical to the probability of any one of these doors on their own, right? That's the probability of your stay, win, and that's a third. The probability of a switch is double that at 2/3. And the idea behind this is that switching is going to win if you chose the wrong door the first time. So the first door you chose, if it's wrong, then switching is going to win. Now, you have a 2/3 chance of being wrong the first time you choose, which means you have a 2/3 chance of winning if you switch. Okay. It sounds confusing for a lot of people, me included, when I first heard this problem. And let me tell you, it's taken me forever to build these slides and make this explanation as not non-ominous, non-crazy as possible. So don't worry if it takes you a minute to absorb all of this. So what happens here is our intuition really fails us because intuition, common sense, it's there for a reason, right? Most of the time, it serves us well. But for certain types of problems, that's not the approach that we need to be taking. And then this is exactly one of those kinds of problems, just like Bertrand's box, just like the 3 prisoners. This takes a little bit more thinking about to get it right. So if you are interested for one of your interactions, what you could do is go to this Monty Hall website, right, and do your own little experiment. So do 10 trials where you stay. Pick a door and then stay with it. Then do another 10 trials where you switch. So pick a door and then switch based on what Monty shows you, right? Record whether or not you win or lose in each of those trials, and then you can compare. You can compare how many wins did I get out of my 10 trials in my stay trials, and how many wins did I get in my switch trials. You could, report your results. You could talk about what they mean. If they don't match what we've been talking about here, in other words, if you get just as many wins for a stay as you do a switch, what does that mean? What does that mean in your data? Right, so that's a good interaction possibility for you guys if you want. Short and sweet and kind of fun. So how do we avoid the scenario of using our intuition in situations where we shouldn't be using it? And we avoid that by knowing the difference between science and not science. And this is where we will pick up in the next lecture in this series. So I will see you guys there.